The early solar system was a tumultuous place, space rocks impacting and colliding with larger bodies to form and shape our contemporary cosmic neighbourhood. But what was the effect of these collisions, and how can we wind the clock back to learn more about the evolution of the solar system? This episode, I spoke to planetary scientist and space rock expert Simone Marchi to find out about the role of collisions in shaping the planets, moons, and other celestial bodies that we know today.
So I'm Simone Marchi, a planetary scientist at the Southwest Research Institute in Colorado, and I study asteroids, planets, the solar system, and how those objects formed.
Yes, no, thanks very much for speaking to me today, Simone. One of the reasons that we're speaking today is because your book is about to come out. At the time of recording, it's about to come out, and it's called Colliding Worlds. And as you know, as a sort of brief synopsis of the book, I suppose would be right to say a sort of history of the solar system via the collisions that have shaped the solar system and the planets and the bodies and other sort of moons and things like that throughout history.
Yes, that is correct. There is what I think it's sort of an untold story, and that is the way it is violent processes through collisions of different objects shaped the formation of the planets, the asteroids, and the solar system, and as we know it today. And so the book unravel all these effects from the beginning of the solar system all the way to modern times.
So what was the early solar system like? Were there more collisions back then than there are today, for example?
Yes, the early solar system was a very, very different place than it is today. Today it's an exceptional event if we were to see a small object, for instance, coming through the atmosphere of the Earth. We call those events falling stars, for instance, and we see those in the summer. And so those are sort of curious events, and there is not much to it in the sense that those are a modest event. It's not like something very energetic. But now, if you all of a sudden go back in time, billions of years ago, things were very, very much different. And we expect that the number of collisions, for instance, that Earth was experiencing was much, much higher than it is today. And so really, the early solar system was a very different place in terms of collisions.
How can we know that? How can we know what the early solar system was like, and specifically just how many collisions were going on?
Yes, there are different ways of answering this question, but really, I would like to bring it back to perhaps the most basic observation. And this brings us back 400 years, the time that Galileo pointed his homemade telescope to the moon, because that is really the key observation. If you just look at the moon as Galileo did, and you can do with the naked eye, without even telescope, you could appreciate that the surface of the moon is not smooth, but in fact, there is lots of round features. So Galileo called those features cavities, because for the lack of a better term, or even in the understanding of how they form, well, we now know that those round features are impact craters. So what they tell us is that the moon, early on in the solar system, was subject to a high and intense flux of collision that shaped the landscape. And now we see that not just on the moon, of course, thanks to the space exploration. We have visited other planets in the solar system, satellites and asteroids, and everywhere we find a rocky surface, we see plenty of impact craters. And so all of this information directly speaks to the fact that early on in the solar system, collision must have been much higher than they are today.
I suppose that brings us on nicely to sort of the question of the history of the moon. Can we sort of decipher with much accuracy as to how the moon formed and sort of how long ago it formed, and did it form via collisions?
Yes, in fact, that is the case. There's been a number of theories that have been proposed over the years as to, regarding to the formation of the moon. But nowadays we are settled on what we call the giant impact hypothesis, this would imply a large object, perhaps as large as Mars or even larger, colliding with the Earth early on, and a result of this collision will produce a disk of debris around the Earth, out of which the Moon will coalesce, that is formed in a relatively short time frame. So the current interpretation is that the Moon was indeed formed through a giant collision. And in fact, this is another great example of the role of collisions in shaping the early solar system. It's not just poking craters on a surface, but it is actually shaping new worlds and creating new worlds such as the Moon.
Given that the Moon is tidally locked, so that one side always faces Earth, does that have an impact in the difference between the near side and the far side in terms of collisions? Are there more collisions on the far side because it's sort of facing out towards Earth, space, for example?
Yes, the current collisional rate of objects striking on the Moon, it's not uniform across the surface. There is an asymmetry. And the asymmetry is actually not between the far side and the near side, but indeed it is between what we call the leading side and the trailing side. Meaning, if you are standing on the Moon, the leading side is the one that faces the direction in which the Moon is going, and the trailing is the other one. And so that is where we actually find an asymmetry. It's not a huge asymmetry, and it's not necessarily the case that this asymmetry was back there in the past. The Moon could have been locked in different orientations, for instance, for some time.
What about other bodies in the solar system? Is it possible to sort of say which bodies, like which planets, for example, have been most affected by collisions throughout the history of the solar system?
It's a hard question to answer precisely for the following reason. When it comes to the other planets, we still have a limited understanding of what their early evolutions were. Consider the following example. We know a lot about the Earth, obviously, because we live on it, and so we can access rocks and materials easily. But the surface of the Earth is strange with respect to many other rocky planets or other objects in the solar system. And the peculiar aspect about the Earth is that it is extremely active in terms of geological evolution. So it turns out that the surface of the Earth is relatively young in terms of, astronomically speaking. There's hardly any portion of the surface of the Earth that's older than 3 billion years ago. So the first 1 billion year, or perhaps even longer, is completely gone on Earth. And so this is a fundamental issue for us to understand the earliest collisional history for the Earth. When it comes to other planets, we have other issues. Take Venus, for instance. We do not have a good understanding of what the age of the surface is. We don't even have a good understanding of the composition. We do have images from the surface radar, images that were able to pierce through the thick atmosphere, but the database that we have, it's not quite enough to fully understand the evolution of the planet. There are lots of mysteries around Venus still. If you go then to Mercury, we have lots of pictures from the surface. We have full map of the surface, and so we see again on Mercury plenty of craters everywhere of all scales, small and large. But we do not have samples, meaning we lack of a precise understanding of what those impacts took place, and so it's hard to reconstruct the history of the planet. And now finally we can get to Mars. Of course, we know a lot about Mars thanks to the space exploration, but still there is a fundamental lack of understanding of, for instance, how old are all those craters that we see on Mars. And so, yes, again, we understand perhaps that there were lots of craters, lots of collisions early on, but it's hard to build a full model that tells us the details of that early evolution. And so we are facing still with lots of challenges.
Mars just always seems to be in the news and sort of like in terms of scientific discoveries and sort of planetary science because we study it so much, don't we? In terms of the rovers and the orbiters, presumably they have helped build a picture of the sort of collision history of Mars and the geology.
Yes, that is certainly true. All the missions from orbit or the rovers has greatly expanded our understanding of the early evolution of Mars. There is no doubt, and there is more to come thanks to the ongoing missions. But in spite of all that, there are still fundamental issues that we know very little about. And just let me give an example. If you look at the picture of Mars, one of perhaps the most striking feature is this what we call the dichotomy between the northern hemisphere and the southern hemisphere. Turns out that the northern hemisphere it's probably the results of a massive collision, what we call the Borealis basin. In fact, the largest impact structure we find in the solar system. And so clearly, that one single event completely altered the evolution of the planet. There's no doubt about that. The magnitude of that event was such to, as we said, erase entirely half of the planet, and most likely also drastically alter the other half of the planet. And so clearly that is an important event. Now, the fundamental question about that event is when did it take place? We don't really know. It would make a huge difference, for instance, if that event took place just right after Mars was formed, or if it took place, say, several hundreds of million years after. Those difference in timing of that formation would imply a very drastic a very different evolution of the planets altogether. And so just knowing the age of that feature is key, and yet we still don't know. So there is hope that with the newer missions, collected more samples, we will definitely be able to address that open question. But that is just an example. Of course, there is many more things about Mars that we are still trying to understand.
Yeah, indeed. And I suppose if you go even further out to sort of the gas giants and then the ice giants, you've got sort of Jupiter and Saturn. I mean, it must be really difficult to get a sort of picture of the collision history of a planet like Jupiter. We can barely even peer through the clouds. Is there anything we can know about sort of Jupiter's collision history?
Oh no, we know very little. We can infer. Perhaps by, those are planets, so Jupiter, for instance, it doesn't have a solid surface. And so you don't see the craters, which is the first thing you would like to see in order to study collisions, right? Because they tell you right away that collisions took place. So we lack that information. Of course, collisions must have taken place after Jupiter formed, but Jupiter is also the largest object in the solar system. So perhaps a collision with smaller asteroids would have been less important. But there are other ways to get at that. For instance, if you start adding, say, asteroids or comets to Jupiter, they may leave behind a chemical trace in the gases. And so these kind of measurements have been done, and there is indication that material could have been added to Jupiter, say, after its formation. But it's an entirely different problem than studying collisions on rocky planets.
Yeah, just speaking of Jupiter there, I had read like a year or two ago about a theory that Jupiter may have sort of moved in the early solar system, sort of closer to the sun and then further. I think it was called the Grand Tack theory.
Yes.
Where do you stand on that?
I mean, there are different ways of understanding the early evolution of the solar system, and different models have been proposed. So the core idea there is that the current structure of the solar system requires that the planets moved around after their formation. So the current model would predict that Jupiter, Saturn, Uranus, and Neptune formed in a much closer and compact configuration. If that's were the case, those close-in planets will become unstable because they'll perturb each other. It's like fighting, gravity pushing things around, and so they want to expand, and that's what they did. When that happened, the system becomes unstable, as we say, and so that is a dramatic event for the evolution of the solar system. And as a result of that, smaller objects such as comets or asteroids would have scattered all around in the solar system. And so the direct outcome of an instability in the solar system is that to produce an increased rate of collisions throughout the solar system and specifically on Earth. So here is where the details of the dynamical evolution of the solar systems are directly connected to the collisional history of, say, the terrestrial planets.
It's really interesting, isn't it? Because when you think about sort of collisions in the solar system, you can sort of say that the solar system wouldn't exist as it is without collisions. But then you could go even further and say that the solar system wouldn't exist at all without collisions, would you? Because isn't that really how planets form? It's sort of cosmic dust sort of coalescing and colliding with each other and getting bigger and bigger over time around its star to create planets. Like, is it safe to say that the solar system wouldn't exist without collisions?
Yeah, I believe that's exactly true, and that is one of the motivation of writing this book, that raveled all that complexity associated with collision from the growing of dust particles all the way to later events once the planets are fully formed. It is what you said is exactly correct. We always think about as gravity is one of the fundamental forces in physics, and of course gravity is what keeps the solar system together, allows the planets to go around the sun, and so it's really the primary process that keeps the system together. But there are many other important processes that, in the end of the day, are perhaps equally important, and collisions is one of them. If you could, by magic, say, turn off collisions, say you would be able to, do something that collisions would never take place, well, then the solar system would not exist, simply because planets, asteroids, everything we see in our solar system is the result of collisions, smaller objects coming together, coalescing, and growing in size. And so if you were able to turn off that process, we wouldn't be here.
When you were writing the book, did you sort of, because that's quite an existential, a sort of almost philosophical point of view in terms of science. When you were writing the book, did you sort of have many moments like that where you sort of had this epiphany, like, oh my goodness, like we wouldn't exist without collisions?
I guess so. There are different levels of that. Yes, but yes, there was this moment in time where I realized that there was this story. It's really about a story, right, about our solar system and ourselves, and there's a story of in the way collision shaped our planets and ourselves, and I realized that was largely an untold story. And so yes, that was a clear point for me that says, yeah, oh my gosh, this is interesting. This is something that it's never been told, and so I would like to write it. And so that was kept me going in this endeavor.
Did you learn much more about our own planet, through your research, other than what you already knew?
Oh, yes, quite a lot. I did say at the beginning that I study planets and asteroids, but really when you start looking at the processes associated with collisions, what it is that the collision could do, it opens a lot of very, very different things. So just to give you a glimpse of that, you may want to understand how meteorites, for instance, can help us understanding early collisions. And when it comes to meteorites, then you are You are in a lab. You are studying, a piece of rock that was formed billions of years ago that landed on Earth, and you are doing chemistry. It's an entirely different thing than when you are looking data from a spacecraft that, for instance, is taking picture of some asteroid, say Vesta or Ceres, in the main belt of asteroids. And so these are very different skills that you need to have. And so definitely it broadened up my range of topics of interest. And there is yet one other aspect that I would like to mention, that we usually think about collisions as say a negative process. Negative in the sense that naturally, if you think about collisions, you end up with a catastrophe. Something violent happened to a planet. And as soon as we start talking about this, the first thing that comes to mind is the demise of the dinosaurs by an asteroid colliding with the Earth. And so there is this negative feeling about collisions. And so it's a little bit depressing. But then as you start digging into that, you'll find out that reality is very different. And there is actually a positive aspect, if you will, about collision. And so that was really new for me, and I really enjoyed digging into that.
You've mentioned quite a few of those missions that have studied, asteroids and comets. So we sort of think about, the current OSIRIS-REx mission and the European Space Agency's Rosetta mission to study Comet 67P. But you've actually been really heavily involved in lots of those missions, haven't you?
Yes, that is correct. I was lucky enough to be involved with several missions, both from the European Space Agency and also from NASA. And I have studied directly, for instance, asteroids. A mission to which I was affiliated. It's called the Dawn mission. It's a NASA mission that visited Vesta and Ceres. These are two largest objects in the main belt. And so that's just one example, but there have been many other missions as well.
Yeah, the really interesting thing about Ceres is it's the only body that we classify as a dwarf planet that isn't sort of beyond Neptune. Do you think it provided a great opportunity to observe a relatively nearby dwarf planet? Do you think that it's worth sending more missions out into the Kuiper Belt? The sort of beyond Neptune, the sort of ring beyond Neptune to look at more objects out there?
Oh, certainly. There is a great deal to be learned by exploring the outer parts of the solar system. So that is certainly true. As well as I would like to send another mission to Ceres if that was possible. There is still a great deal of interest in science that could be done there as well. So yes, all of those options will be great.
Yeah, because you often hear people sort of talking about comets and asteroids as being like the sort of relics of the solar system. They're sort of why is that? Why are they so important in knowing what the early solar system was like?
Yeah, it's an interesting aspect because when you look at an asteroid, you see a small object, right? Asteroids have sizes ranging from very, very tiny, it could be a meter, all the way to Ceres says this is about thousands of kilometers across, and if you go in the outer solar system, you have even larger objects. Now, but those are still relatively small compared to larger planets, say the Earth. And so the question that we get asked a lot is, why do you care about these little things? Are they, because they're small, are they then negligible to the bigger picture, right? This is a legitimate question. And the answer to that question is that no, they are not negligible. In fact, it turns out they are very, very important for a fundamental reason. Let's now consider, for instance, the asteroids that are closer to Earth. Those objects are the leftover, if you will, of the process of planetary accretion. So you can imagine the Earth and other planets grew up out of a disk of debris, smaller asteroids, and many of them accreted to form the Earth. But as you start doing that process, those objects are going to be heavily altered. They are chemically altered. They are molten, and then they resolidify, and so they pristine materials are completely transformed in something new, and so the information about the earliest material is perhaps lost. Now, the leftover of that process are small asteroids that still orbit the sun. And Vesta, for instance, and Sirius are good examples. And those objects were not incorporated into larger planets. In other words, they kept, in virtue of their small size, they kept their primordial properties. Of course, there has been some alteration on those objects as well, but the point is that they are not so drastically altered like a larger object. So it turns out that these leftover, smaller objects are indeed very important to understand the formation of the solar system. And there is one key observation that I would like to throw in there. In fact, the age of the solar system, it's not determined by measuring the age of the Earth. It is determined by measuring the oldest meteorites that we find on Earth. And so that tells you directly that, for instance, if you want to know when the solar system formed, you shouldn't be looking at the Earth, but you want to look at this meteorites that comes from asteroids.
You must be really excited about the OSIRIS-REx mission and the Japan's Hayabusa 2 mission, which, in case anyone doesn't know, are actually going to return asteroid samples to Earth. That's just absolutely incredible, isn't it? That we're actually going to have asteroid samples on Earth that we can study.
Yeah, that is an incredible feat, being able to go to an asteroid that we have already done in the past. But now the next step is to be able to interact with the surface, grab samples from the surface, and bring those samples back. And so that is really something that is extremely important. Of course, we have done something like that with the Apollo missions back, with the early days of the lunar exploration. But now the future is to expand in their capabilities to other objects in the solar system, asteroids, and one day Mars.
It's absolutely fascinating. I mean, just to finish, I'm just going to finish with a question that may make you roll your eyes, being interested in planetary collisions and collisions in the solar system. I'm sure you get asked this all the time, but what's your sort of view on the likelihood of a sort of major level impact on Earth and sort of the sort of detrimental effect that might have on life on Earth? First of all, do you get asked that all the time, and what's your sort of answer?
Yeah, that's a really common question, and the answer is it's not a straightforward answer in the sense that the Earth gets collisions every day. For the most part, these are in form of tiny dust grains that comes through the atmosphere, and so we don't notice that. Occasionally, we get a larger fireball coming through the atmosphere, but really the question is, what is the likelihood of having yet something larger coming through the atmosphere, something that could potentially be dangerous for us? So the probability of having, say, a larger object, something of the order of a kilometer or even larger, colliding with the Earth are basically nearly zero. And we know that because we have a precise knowledge of all the objects close to the Earth of that large size, and we know that there's none of them potentially in route, in collision with the Earth. And so we shouldn't really be thinking of something like the dinosaur killing event happening again in the near future. I think chances are pretty slim for that. However, there is a class of objects that are smaller than that, say tens of meters, perhaps even 100 meters, that sort of size range, which are not tiny, negligible, if you will, but they're not super large that would wipe out the surface of the Earth all at once. So in that intermediate size range, which is the most dangerous potentially, because we do not know a detailed knowledge of all the objects out there of that tiny size, because they're hard to observe. And so in principle, there is a possibility that there is an object of that size range that could come through the atmosphere. Now, those objects are not going to wipe out the entire surface of the Earth all at once because they're too small for that. But still, if they were to collide on a major city, they could produce significant local damage. Now, chances of that are extremely small, so we shouldn't really be worried about that. But it is a good reminder for space agencies to keep looking for objects out there, unknown objects of that size range, in order to have a full understanding how many are there, and so that's the first step in order to be fully informed.
I suppose that's at least one advantage we have over the dinosaurs, is that the dinosaurs didn't have telescopes or a space program.
Yes, that's right. Now, of course, I want to say that if we were to find out that the 10-kilometer asteroid is coming towards us, we wouldn't stand any hope of deflecting, of doing anything with it, because it's simply too large. So, we will know that's coming, but then we'll have to brace, and, we wouldn't be able to do much with it. But we could potentially do something with the smaller objects coming towards the Earth if we knew well in advance.
Well, on that note, I think that's about all the time we have, Simone. But I just want to say thanks very much for speaking to me, and good luck with the book when it comes out. And yeah, it's been great to speak to you today.
Thank you, Ian. Thank you so much for having me here. My pleasure.